On February 23rd, 1987, an explosion rocked the sky that was unlike anything anyone had seen, not just in living memory, but in centuries. If you had a keen eye and lived in the southern hemisphere, you could step outside on a clear night and witness a bright dot that wasn't there before. It's as if a new star appeared. But it wasn't a new star, though. It was a supernova, one of the most violent events that can happen in our universe. And it was the first supernova to be visible to the naked eye since the telescope was invented. In the decades since, researchers have learned an astronomical amount of new science by studying this one explosion. I'm talking right up until 2023, when they finally solved the mystery of what it left behind. Nothing lasts forever, including stars. And the reason they're shining in the first place is they're using up a bunch of nuclear fuel inside of them. And as anyone who's had to worry about surging gas prices or getting hangry knows, fuel inevitably runs out. But while some stars, like our own sun, are content to just end their lives with a proverbial whimper, others go out with a bang, a near-instant, massive explosion that tears the star apart. Our galaxy is supposed to have 2 to 3 of these supernovas every century, but most of the time we can't see them from Earth. They're often too far away with too much interstellar dust in the way. That's why the previous great supernova, one that like an average person could step outside and spot without a telescope, was seen all the way back in 1604. But luckily for astronomers, there are super fancy telescopes that let them look at millions of other galaxies and hunt for supernovas that are way too dim to see otherwise. And the one that happened in 1987 did happen in another galaxy. Sure, it's the Large Magellanic Cloud, which is a dwarf galaxy on the Milky Way's back porch, but it counts. And at roughly 160,000 light years away from us, the light from the supernova had 160,000 years to spread out as it traveled through space, which is why it was a lot less bright than that 1604 explosion. But what it lacked in visual brilliance, it made up for as a brilliant bedtime story. Early in the morning on February 24th at Las Campanas Observatory, high atop a Chilean mountain, astronomer Ian Shelton was developing his final photographic plate of the night. And as he scanned the image captured on that plate, he saw a star that didn't used to be there. He rushed outside to check, and to his surprise, he could see this new star with his own eyes in the night sky. Of course, Sheldon hadn't witnessed a star being born. It was the opposite, and he and his colleagues scrambled to get a message to the International Astronomical Union, which involved a 100-kilometer drive to the nearest town. Oh, and because astronomers are so amazing at naming things, they eventually gave this once-in-many-lifetime supernova a very catchy name, SN 1987A. Eventually, astronomers were able to pin down exactly which star in the sky went boom. It went by the name, this, and it was roughly 20 times more massive than our sun. Now, being so massive, you might think that it'd be able to live a lot longer than our sun will, but for stars, it's actually the opposite. The more mass you've got, the faster you burn through your fuel. So while our sun is roughly halfway through its 10 billion year life cycle, the progenitor to SN 1987A kicked the astronomical bucket at the ripe old age of only 10 million years. Of course, the supernova at the end of its life was even more of a pinprick in the greater timeline of the universe. The winds of change started about 1 million years before the actual explosion. The star's core ran out of its primary fuel source, hydrogen, and with no way to spew out a bunch of energy, it started collapsing under its own gravity. But that near collapse actually helped the star switch over to burning the next lightest thing available, helium, but eventually it ran out of helium too. So it switched to another fuel, and then this happened again and again until there was nothing left that the star could use, and its nuclear furnace turned off. And at that point, gravity took over one final time. In just a few tenths of a second, the core collapsed down from being roughly Earth-sized to a sphere the size of a small city, creating a stupendously powerful shockwave that ripped the star apart. And over the next few months, that explosion released as much energy as our sun does over 100 million years. In fact, it peaked in brightness a full 3 months after astronomers first detected it. We'll get back to why that happened later, but 160,000 years after that initial explosion, all that light finally reached the Earth, including Dr. Shelton's photographic plate. But after that momentous night in the Chilean mountains, astronomers realized there was another signal from the supernova that had arrived just a bit earlier, and it was much weirder.
This episode is brought to you by this month's presidents of science, McLaren Stanley and Charlie Stanley. How can there be 2 presidents? Democracy. Maybe we should rename it. Leave your suggestions in the comments. Anyway, thank you both for being so awesome and supporting us over on Patreon. If you, dear viewer, want to learn more about becoming president of science or about one of our other wonderful patron tiers, go to patreon.com/SciShow.
In the seconds surrounding the final collapse, the nuclei in the star's core went through one final sudden nuclear reaction, which produced a burst of odd, obscure particles called neutrinos. These fundamental particles are infamous for having almost zero interaction with other kinds of matter. Like, while a high-energy particle of light is stopped by a few centimeters of lead shielding, you'd need a wall that's around a light-year thick to stop an average neutrino. So it's basically impossible to capture a single neutrino in even the fanciest neutrino detector. But if you've got enough of them streaming through space, statistics wins out. So in 1987, a few hours before the light of the supernova reached Earth, neutrino observatories around the world noticed a distinct spike in detections. And since that spike happened in one precise moment in time, it suggested that there was a sudden wave of neutrinos generated by a single event that had just passed through Earth. And the cool thing is, there was a tiny bit of luck here. Neutrinos had been known about for like a few decades, but neutrino detectors were very recent inventions. So if the supernova had happened like 20 years earlier, which is nothing to the universe, we wouldn't have picked up this part of the signal at all. But wait, why did the neutrinos arrive before the light from the explosion? Were the neutrinos traveling faster than light? Well, no. In fact, it was the other way around. The light was traveling slower than light, or rather, how fast light could travel in the dead void of space. Remember, neutrinos can pass through basically anything unscathed, so as soon as they were created, they could zip straight through the collapsing star and the surrounding gas with nary a care. Meanwhile, the light produced by the supernova had to push through all that stellar matter before it could escape into interstellar space. So to an observer on Earth, it looked like the neutrinos had gotten a head start, and the fact that they had arrived a few hours ahead after a journey of 160,000 years proved that the neutrinos must travel extremely close to light speed. In other words, SN 1987A was yet another key piece of evidence supporting Einstein's theory of relativity. But that wasn't all we learned. SN 1987A was the first major supernova in modern astronomy, even if you define modern as after people started using telescopes. Plus, since it was also the 80s, scientists had a fleet of high-accuracy telescopes, not just around the world, but in space too. So after word got out, countless people aimed their equipment at the exact same spot in space, staring down the supernova remnant in the Large Magellanic Cloud. And over the past several decades, SN 1987A has revealed a lot about how supernovas work. For example, astronomers learned that they were generally correct about how stars undergo core collapse. But it also showed that a few supernova theories weren't quite right. Remember how astronomers were able to identify the star that exploded? Well, it was a blue supergiant. But up until that point, astronomers had only ever attributed supernovas to their much larger cousins, the red supergiants. Basically, they thought that a collapsing blue star, like SN 1987A's progenitor, wouldn't be able to create the signals that they were detecting from those other supernova remnants. And while it is true that most core collapse supernovas do come from red supergiants, SN 1987A showed that they don't have to. Astronomers also realized that before a star dies, it can eject way more matter than they thought. SN 1987A's blue supergiant progenitor spent its last several thousand years shedding the plasma in its outer layers. And before that big kaboom, that debris had built up into a ring spanning about a light year in diameter. When the supernova finally happened, all that light slammed into that ring, causing it to glow with X-ray light. And in 2010, the Hubble Space Telescope detected that this ring was getting brighter, producing a structure that media outlets likened to a pearl necklace. While the specific interaction did match what astronomers predicted would happen, some of the latest images have features that astronomers don't quite understand, like structures that they think might be caused by what they call reverse shock waves. So it's a bit of a mixed record for SN 1987A confirming and denying theories about supernovas. But in 2024, the biggest mystery of them all may have been solved. See, ever since astronomers accepted that this new star was in fact a newly dead star, there's been a debate about what exactly happened to the star's corpse after the explosion. Namely, which of the two most extreme objects in the universe did the core collapse into? A neutron star or a black hole? Both of them are observed in other supernova remnants, so either one's possible. But the problem is, for decades, no one could find anything. So maybe the explosion was so violent there was no remnant. Or maybe the remnant was something completely unseen before in nature, some exotic midpoint between a neutron star and a black hole called a quark star. Or maybe it was just hiding behind a bunch of dust. Hints that it was probably just a regular old neutron star started trickling in a few years ago. We even covered the news over on SciShow Space. But when the JWST came online in 2022, it could use its infrared detectors to peer through all that dust with unprecedented detail, and so astronomers appear to have finally settled the matter. According to NASA, the telescope found the telltale signs of a newly birthed neutron star. So as incredible as that stellar implosion was, it didn't quite have enough strength to crush the core all the way down to a black hole. Instead, the core became a hyperdense ball of solid nuclear matter, held up by the most extreme force in the universe. But we've barely scraped the surface of the treasure trove of data that SN 1987A left behind. It gave astronomers better estimates of how far away the Large Magellanic Cloud is, how fast the universe is expanding, and where the dust in galaxies comes from. But perhaps most importantly, it also fired up the public's imagination. The supernova was even featured on the cover of Time magazine, and I, for one, think it totally deserved it. This supernova was a reminder that despite how fleeting our lives are to the greater cosmos, we can still see major moments of change. We live in a dynamic, evolving, ever-changing universe, and that's as good a reason as any to keep looking up. And you know what? The supernova remnant left behind will also change as time marches forward. JWST didn't see the same shape that Hubble captured in decades past, and whatever the next-gen space telescope decides to take a peek, it'll look different again. So when our merch team had to design our latest pin, they had to pick which version of the supernova to go with. They went with this image inspired by JWST. If you'd like a tiny supernova remnant to call your own, you can head on over to complexly.store/SciShow and pre-order yours today. Thanks for watching.